Assalamualaikum and hi everyone. My name is Nur Shakila binti Azizan and my number matric is 24109129. So today I want to present about the lab 2, that is operational amplifier by using LT Spice. So for my part, I want to present about the three operational amplifier, that is inverting, non-inverting and summing amplifier. So the goal is to observe how this circuit amplify the signal, compare the theoretical calculation and with the real measurement, and understand how the output waveform behave in the practice. Now I want to show the first configuration, that is inverting amplifier. This is the circuit for inverting amplifier. So R1 we use 1 k ohm, R2 is 33 k ohm, V peak is 1 volt and the frequency is 1 kilohertz. So the output when we measure is inverted, meaning the sine wave is flipped upside down. So when the peak were positive in input, that become negative in output because it is show 180 phase shift. The theoretical gain that we calculate is negative 33. Now let we simulate the inverting amplifier circuit to see the result. So this is the result for V out for inverting amplifier, that is negative 13.97 volt. So the calculation data is negative 33 volt, but the V out that we get is negative 13.97 volt because the LM471 is have the limit. So when have the limit, the waveform may be clipping. We can see the waveform is clipping at the negative peaks because the LM74 cannot be on its supply limits. So now I want to present the second part, that is non-inverting amplifier. For R1 I use 1K, R2 10K, and for frequency and V peak same also with inverting amplifier. So when we measure, the output stay in phase with the input. The waveform shape is same, but the amplitude for V out is 11, and this is because the high input resistance ensure the input signal is not affected. So now let me see the result for non-inverting amplifier. So we can see the result is 10.997 volt. So the calculation is 11 volt. So the result for measurement and calculation is matched. So we can see the waveform shape is also same, sine wave waveform, and no clipping because not achieve the limit. This the waveform is in the same phase. Now let we move to the third part, that is summing amplifier. So for R1 is 10K, R2 is 2K, and RF is 10K. So for the both input, we use 1 volt peak, and the output waveform is weak. Some of the two input and the peak are higher depending on the resistor ratio and producing a combined sine wave. So now let me see for the summing amplifier result. So this is the result that I get is negative 5.98 volt and the calculation is negative 6. So the result is same with the measurement. After that, we can see the waveform for input and output is sine wave. But if the input is positive, the output is become negative. So what we can conclude for the simulation part is, for the simulation part, we can see the waveform characteristic clearly. For the inverting part, the waveform is inverted. For the non-inverting part, the waveform is same. And the last is sum peak for the summing amplifier. So what we can conclude for the result is different from the theory is because a practical limit of the OM, including the output or voltage range, input offset, and the loading effects, using a proper resistor value and input voltage to ensure the correct operation. The next part is principle based on the understanding. Based on the understanding, if the output more than the power supply, if the signal try to go above that, it's clip flattening the waveform at the maximum or minimum voltage. After that, for the inverting amplifier, the output waveform is flipped. Too much gain may cause the clipping. After that, for the non-inverting amplifier, the output waveform stay in the same direction with the input, but the amplitude is increased, but the same shape is have. After that, for the summing amplifier, the output waveform is combined effect of all input together, and the resistor ratio determine the height of the peak. So for the understanding, this simple rule help the predict waveform behavior and can explain the difference between the theory and the measurement result. For the conclusion part, that what we can conclude is, for the inverting amplifier, invert the waveform and may clip at the high gain. After that, for the second is inverting amplifier waveform. When we simulate, we can get the same same shape of waveform and the same pace. After that, for the third is summing amplifier, accurately combine the input waveform when we design properly. After that, from the circuit that we do, what we can observe is the waveform help to understand the practical op-amp behavior, and we can see the difference between the ideal calculation and the real circuit, and what is important is to choosing the proper resistor value and the input level for the accurate amplification. Next, I pass to my partner to continue next part. That's all from me. Thank you.
Assalamualaikum, my name is Nurul Fatati binti Waslan. Entry number 241091210. Today I present the integrator and differentiator of heat and fire. The main objective of this lab is firstly to understand how heat and fire circuit perform the mathematical operation on signal. Secondly, to compare the voltage output value in theory and simulation. Lastly, to identify how non-ideal OP and fire characteristic affect real circuit behavior. Firstly we'll start with the integrator. This is integrator OP and fire. The main component is LM741, and then we have feedback resistor parallel with the capacitor to give stability to the circuit. And for voltage input, we set 1 Vpeak, 1 kHz frequency in the square waveform. This is the calculation for voltage output integrator of fire, which we get negative 1 volt. For the simulation value, we will measure here at the voltage output at the triangular waveform. We add the cursor. For the voltage output simulation value, for the voltage output, we get 3.0381578 voltage, which is different from the calculation value. There are a few reasons why the calculation value and theory calculation value and simulation value different. Firstly, because of DC offset. Any small DC component is integrated continuously, causing the output to drift outward. Secondly, input bias current. This current slowly charges the capacitor, increasing the amplitude. Third, finite bandwidth and slew rate. The op amplifier cannot follow the ideal square wave perfectly, modifying the slope of the triangle wave. And lastly, this is in our lab, this is a practical op amplifier, which means this value is for practical op amplifier. Meanwhile, for the calculation is for the ideal op amplifier. That's why the calculation value and the simulation value is different. And next we will move to the differentiator of amplifier. This is the circuit for differentiator of amplifier. The main component is same, LM741. RF is parallel with the capacitor to give stability to the circuit. And then for the voltage input, we set 1 Vpeak, 1 kHz frequency in the triangular waveform, which means the input will be triangular waveform. And this is voltage output differentiator of amplifier. For the calculation, we get negative 1, and we can expect a square-like waveform in output. Here is the voltage output for the differentiator of OP amplifier. The value for the simulation is, as you can see here, the value for simulation is 4.0110723 volt, which means it's different from the calculation value. There are a few reasons why there's difference between simulation and calculation value. Firstly, because the differentiator amplifies loop, not signal amplitude. Secondly, the triangular input signal has steeper slope than assumed in theory, causing a larger derivative. And lastly, the circuit amplifies high frequency excitation and noise. Because of this, the simulation value for voltage output and calculation value is different. In calculus concept, integrator output ramps up because the integral of a constant is a linear slope. Meanwhile, the differentiator output becomes square-like because the derivative of triangular wave is constant. This means more DC offset means more drift in integrator. Higher dB per dt means larger differentiator output. Higher frequency means more sensitive output due to the op amplifier limitation. In conclusion, this lab successfully demonstrates how integrator and differentiator circuit behave in real condition. The integrator produces a triangular waveform and differentiator produces a square-like waveform conforming the mathematical function. However, the major amplitude are higher than calculated due to the DC offset, bias current, dB per dt sensitivity, and non-ideal op amplifier constraint. That's all for me. Thank you.